We've learned how the Standard International Bureau of Weights and Means has come to define basic units for fundamental quantities of length, and they do that based on the speed of light, and time they measure with the oscillations of cesium atoms. Now we're coming to our friend mass. How do they define the SI unit of mass, which here is the kilogram? Well, this is quite a fundamental quantity, and as such, it turned out to be that it was actually not so easy to find a consistent definition for the unit of mass being a kilogram. Originally, it was defined to be the weight of 1 liter of water. Here's a liter of water. It's 0.1 meters on a side. A cube, 0.1 meters on a side, is a liter of water. And that weighs a kilogram, roughly a kilogram. So why then did they switch to defining the kilogram as the weight of this thing here? They called it Legrand. They have it at the French Bureau of Weights and Means. It was a platinum iridium cylinder. Well, this stuff, platinum iridium, my guess is this stuff is quite stable, not chemically reactive, doesn't lose any weight, and so they defined mass to be the weight of this platinum iridium cylinder. But embarrassingly, this thing lost some weight, like some nanograms over time, even though they're real careful with it. Well, how in the world did they figure out that this thing lost weight if it was the standard by which the kilogram was determined? Well, obviously they had something else better, and now they're using that. They're calling it a kilobalance, and this is measuring weight. It's measuring weight as an interplay, fundamental interplay of forces of nature. Yeah, it's a fundamental interplay of forces of gravity and electrodynamics, and they're combining these, if you will, into a very sophisticated balance that measures a weight based on the interplay of these forces of nature. And when it comes down to how they resolve the weight balance, this thing called Planck's constant naturally comes into play. The Planck constant. What is the Planck constant? This is actually a quantum mechanical effect. Planck himself derived the constant when he was solving the so-called ultraviolet catastrophe problem. So back in the day, they were measuring electromagnetic spectrum, and it acted like they thought it should from classical mechanics up to a point where the theory broke down, the classical theory broke down. And Planck came along and figured out, well, if he treats the energy levels of electrons, the electron states, as being quantized and separated by this value of the Planck constant, so the energy of electrons just steps in jump steps of the size of the Planck constant. So here's this quantum mechanical thing. And so he solved the ultraviolet catastrophe. So this is a constant of nature, and why is that good? To have something that bakes down to a constant of nature when you're deriving the standard? Well, just like we were saying before, constants of nature don't change around. Like, is water a constant of nature? Well, if you have a liter of water, what's the problem with that? Water's pretty reactive stuff. It's going to be hard to keep it pure. It's going to want to take on impurities quite easily, and it may react with something, and that's going to give it impurities. So I think it was clear to say that all along they were looking for something like this kilobalance, and now we've got it. So good news. But meanwhile, we're talking about constants of nature. How do these things go together? So here we have a mass of water, and that mass of water is a kilogram, and it's coming in this 1 meter cube. Now we've defined the SI unit of length is equal to the meter. But what is the SI unit of volume? Okay, so the SI unit of volume, which we'll just call V, the SI unit for that is meters cubed. And remember, when we put these brackets around something, what I'm saying by putting the brackets around it is just grab the units, man. So just grab the units of L. Well, the units of L and SI are meters. I say, okay, here's a volume, just grab the meters. So why are the units of volume meters cubed? Well, you can see to get a volume, what do? You multiply a length. So let's say each of these has the same length, L, L by L by L. So L cubed here, in this case, L is a 0.1 meter, as you can see. So the units of L cubed are meters cubed. Now let me ask you this. What do you think is more fundamental? a volume or a length? I would submit to you that a volume is a more fundamental physical quantity than a length. Why is that? Well, try to imagine something, which is a mass of any kind, that doesn't have a volume. Think of the smallest stable bit of mass. The smallest stable bit of mass I know of is the electron. And once you have that electron, what is that electron doing? It's occupying volume. It takes up three-dimensional space. It takes space up. So I would submit to you that the volume is an even more fundamental quantity than the length, which we measure in meters. So why is our base unit in SI cracking down? Why is the most fundamental unit cracking down to meters, and a composite unit that we're building up from that is a volume, meters cubed, right? You can see the units for volume are a composite of units for meters. It's meters times meters times meters. And we're going to see a lot of units come up like that. They're composites of SI units. They're constructions built up from conglomerations of SI units, if you will. And I'm just telling you that the volume is even more fundamental than the meter. Well, and whether we can agree on that or not, or whether it's true, why is the meter defined to be a fundamental unit? Well, it's because it's how it's measured. The units themselves are joined at the hip with how they're measured. For the most fundamental quantities, there literally is no difference between them. Okay, so we have the units of volume. And we could try doing some conversions with this. By the way, if I split this up into 10 parts here, let's say we go like this, all the way up to 10. So L is 0.1 meter. If we do that, then the distance between each one of these little tick marks will be a centimeter. How could I know that? If we look at the distance between one of these ticks right here, the length of that tick is 0.1 meters. That's this whole distance. And I've divided it up so that there's 10 of them. And that is equal to 1 centimeter. So 1 centimeter is equal to 0.1 meters. So let's ask this question. What is this volume? Let's first ask it, what is the volume in cubic meters? Well, the answer to that is it's, okay, L cubed. 0.1 meters cubed. And it's actually more convenient to write this in scientific notation. 10 to the minus 1 meters cubed. And I'll show you why right here. Because now when I cube everything, what's 10 to the minus 1 cubed is 10 to the minus 3. So here we have our volume. We could ask this question. And by the way, this is 1 liter of water. This is also, by definition, a liter of water is a cube of water that's 0.1 meters on a side. So if you make a cube and the sides of that cube are 0.1 meters, that is a liter. Now the question I have is, what is this liter, this volume of 1 liter, what would it be expressed in cubic centimeters? I know right here the 1 liter is 10 to the minus 3 cubic meters, and if you weren't sure, that is 1 over 10 to the 3 meters cubed, which would also be equal to 1 over 1,000 meters cubed. What is this expressed in cubic centimeters? To do that, what we'll need is to use our conversion factors. So here we can see we've already cooked up a conversion factor over here. By definition, 1 centimeter is equal to 0.01 meters. Or if I want, I could write it this way. I could multiply both sides by 100. This 0.01 is actually 1 over 100. 100 centimeters is equal to 1 meter. I want to convert this liter right here, 10 to the minus 3 cubic meters, into units of cubic centimeters. So how do I do that? Well, what I can do is if I make a conversion factor right here like this, if I make a 1, magic 1 is equal to, say, 1 meter over 10 to the 2 centimeters, because 100 is 10 to the 2, and then multiply this magic 1 by this 1 liter over here, or multiply it on the right-hand side. That will not do the job for me because, well, I'd have to flip this around anyway. It's just as legit to write it this way. So now if I multiplied this expression here, let's just go ahead and do it. If I multiply like that, then we could see this meter will only cancel with one of these, and it would make that a 2. And that's not what we want to do. So what we want to do to get this thing to work then is cube this whole expression in parentheses right here. If we cube that whole thing, then what will happen is you'll have 10 to the minus 3 meters cubed times, now inside here, this cube thing here, this 3 goes on to every term in here. So 10 to the 2 cubed is 10 to the 6 centimeters cubed over meters cubed. Then now we get meters cubed canceling with meters cubed, and we're going to be left off overall with just units of centimeters cubed. So we're going to have 1 liter is equal to 10 to the minus 3 times 10 to the 6. So if I'm multiplying 10 to the minus 3 times 10 to the 6, then these exponents add, and I'm just left with 6 minus 3 is 3, 10 to the 3, 1,000. This is here 1 over 1,000 times a million, so a million divided by 1,000 is 1,000, and the units are cubic centimeters. Does that make sense? Okay, that's telling us that in this cubic liter there are 1,000 cubic centimeters. Let's see if that makes sense. If I look over here and I say I slice this up, so I slice this whole thing up across this way, 1, 2, 3, and then the last one over here would be 10. It's not really drawn to scale that well because it's a little bit sloppy here. But let's see, look at it this way, and that would be 1, 2, again all the way, the last one over here will be 10, again over here. So if we look at how many cubic centimeters we'll have here, on the first face we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'd have 10 cubic centimeters along this top bit. Those would have that size right here. So we're doing the same thing here. 1, 2, all the way down to 10 down there. And then here's each one of these would kind of look like that. So we look here, okay, just count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 of them going that way. And then count this way, so 10. And then you have that times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 times 10, and that would just get you this first slice here on the top from here to here. And in that slice you have 10 times 10, that's 100 of them. And then now you count, how many of those do you have? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. So you have 10 times 10 times 10. So you're right, there's 100 of these, and then you got 10 times of that. So 100 times 10 is 1,000. So you can see there's going to be 1,000 cubic centimeters in a liter. So as you may be aware, it turns out to be pretty useful to express some numbers in scientific notation. That is, to express them as some number here, some real number, times 10 raised to a power. So it's some number and then an order of magnitude. The order of magnitude is 10 raised to the power. Here the order of magnitude is 9, 10 to the 9. And what do we have here? We have 1.27 times 10 to the 9 watts. That is 1.27 billion watts. 10 to the 9 is a billion. Or another way we could write it is just putting this letter in here for it, giga. That letter literally stands for 10 to the 9. So 1.27 times 10 to the 9 watts is equal to 1.27 gigawatts. And we would not want to write this number as 127 followed by 7 zeros after it, or move this decimal place 9 times. And you can see this definitely compacts the notation, abbreviates the notation. And you can always replace these letters with the numbers that they stand for. So some common ones, the ones we're going to be using all the time, are like this one over here, the centa, 10 to the minus 2. We've already seen that that one is useful for writing centimeters. So if we write 50 centimeters, we could convert that directly into meters. Well, you could move the decimal place twice. Another way to convert this directly into meters would just be to replace this C with what it stands for. It stands for 10 to the minus 2. 50 times 10 to the minus 2 meters. And now if we wanted, we could use the 10 to the minus 2 to move the decimal place twice. So makes that 0.5 meters. Another pretty common one we're going to be using a lot is this one here, the kilo. Let's say we had 150 kilograms. We could convert that directly to grams just by replacing this K with what it stands for, 10 to the 3. 10 to the 3 grams, which we could write in scientific notation as 1.5 times 10 to the 5 grams.